In this video, we will try to define the concept of stability a bit more clearly than we have done so far. We'll talk about what it means for an IVP to be stable and what conditions there are for numerical solutions of IVPs to be stable as well. Let's first define stability. Now, we can say that a physical system is stable if small perturbation on the parameters, such as coefficients or initial conditions, result in a small difference in the solution. Or we can define it on the contrary, that unstable systems are systems where small perturbations cause large differences in solutions, which may even blow up or become oscillatory or very, very large. And some examples of unstable systems are shown here in the slide. And on the left, we have a so-called double pendulum. And let me start this animation. Now, in this double pendulum animation, well, there are three different pendulums simulated with three very slightly different initial conditions. And they have different colors, blue, green, and red. Now we see that although they start out similarly, after a short while, this small perturbation on the initial condition results in them, well, having completely different trajectories after some time. And this is what we call a chaotic system, which has extreme sensitivity to initial conditions, which is also related to this famous butterfly effect in chaotic systems. Another example of an unstable system is the well-known Tacoma Narrows Bridge, where a unstable torsion mode was excited by a wind load, which in the end led to the collapse of this bridge, of this suspension bridge. Let's look at the movie here, and we see that initially, well, there are some oscillatory movements of the bridge. However, these oscillations, well, they start increasing in magnitudes. I think at this point, we can clearly call this an unstable system, as these oscillations keep on increasing and increasing, and they will eventually lead to the full collapse of the bridge. So we see here that this torsion mode gets excited more and more until the bridge collapses. So that's also an example of an unstable system, which is highly undesirable, of course. Now let's look at it from a more mathematical point of view when we're specifically talking about initial value problems. And let's define the stability of an initial value problem. So let's say that we have an original initial value problem consisting of this ordinary differential equation equipped with also a initial condition. So this initial value problem. And let's say that, assume that there is an error, a small error, epsilon 0, on the initial condition, which results in a perturbation, a perturbed solution. Now this perturbed solution, well, that will satisfy the following initial value problem. So the initial condition is slightly different. The function f itself, well, that is what governs the system dynamics. That's like your Newton's second law or your chemical reaction. So that those governing equations are not really modified by this perturbation on the initial condition. So that stays the same. So we find that this perturbed solution y tilde follows the following initial value problem. So the same ODE, but with a slightly different initial condition. Now, let's define the difference between the perturbed solution and the original solution as follows, as epsilon is, well, the perturbed minus the original solution. Then we define that the IVP is stable if this difference will stay smaller, well, will stay finite, let's say, for all x. So no matter how large x gets, that this difference doesn't grow unboundedly, so that it stays finite. And we call it absolutely stable if this difference between the perturbed and the original solution, if that difference decays as x goes to infinity. So if this difference, let's say, dissipates the longer we integrate the ordinary differential equation, or the IVP. Now note that this is stability of the analytical IVP itself. And well, that leads to these conditions. But that does not directly imply the stability of the numerical solution obtained from a given numerical method. And that's a different question altogether, one that we will also try to answer in the following slides. Now let's look at a specific IVP called the test equation. And the test equation, we've already encountered it earlier in this lecture, but it looks like this. So we have that the derivative of y with respect to x is a constant lambda times y. And we have an initial condition where y at x is 0 is y0. We also consider a perturbed test equation where simply the initial condition is perturbed slightly with this small epsilon 0, but the ordinary differential equation followed by this perturbed solution y tilde is the same. So we have in the right hand side lambda times y tilde. Now we can easily solve these initial value problems. You can solve them analytically, separation of variables. It's very straightforward. So the solution to the original equation, well, that's simply y naught times e to the power lambda x. That's for the original one. For the perturbed one, well, the only difference is this constant over here. So y naught plus epsilon naught times e to the power lambda x. And you can verify that this satisfies those equations and the initial conditions. Now we can check the difference between the perturbed and the original solution. And you can see that, well, this y naught contribution drops out. And what is left is this epsilon naught, so this small initial perturbation on the initial conditions, multiplied with e to the power lambda x. So what does this mean? Well, it is the IVP is stable if for all possible x, epsilon x remains finite. Now, if we increase x, let it go to infinity, then we see that if lambda is positive, if it is larger than 0, that this epsilon x will also go to infinity. So a condition for stability here is that lambda has to be smaller than or equal to 0. If it is equal to 0, then this difference is constant. This becomes 1, and the difference is always equal to this small initial perturbation epsilon 0. If lambda is smaller than 0, then we have what is actually absolute stability. Then this perturbation, or the difference between the perturbed and the original solution, will decay as we increase x. So important here is that if lambda is smaller than 0 or equal to 0, we have a stable IVP, so that the analytical test equation is stable. Let's now look at what happens if we apply numerical algorithms to this test equation and what remains of the stability of the numerical solution to the test equation. Okay, so we know that the IVP is analytically stable for lambda smaller or equal to 0. So let's assume that the IVP is stable. So we assume that lambda is smaller than or equal to 0. Here we have our original system, the perturbed system, and let's apply explicit Euler to both of these systems. Well, explicit Euler is straightforward, so we update the solution from step I to step I plus 1 by adding h times, well, a slope which is governed by the right-hand side of the ODE evaluated at step I. So this is lambda times yi. And we can write this as 1 plus h lambda times yi. Similarly, for the perturbed solution, well, we can also write this one as y tilde and in step I plus 1 is y tilde in step I times 1 plus h times lambda. So we can subtract these from each other. And you can work it out. It's very straightforward. And you find actually that the numerical, let's say, or the perturbation on the numerical solution, so this epsilon in step I plus 1, or the difference between the perturbed and the original solution in step I plus 1, well, that is also following this relationship, so that it is the perturbation in step I multiplied with 1 plus h lambda. And that follows simply by subtracting this from this. Okay, so what we see here is we have a factor here, and we call this the amplification factor, which is a function of the step length h and the let's say this constant lambda that goes with the in the right-hand side of the ordinary differential equation. Now we know that this lambda is smaller than or equal to 0. So this is this amplification factor. Now we can say that, well, in order for this epsilon to remain bounded, so for if this is to remain bounded for all possible I, so if we keep on increasing our horizon of integration, this is only stable if the absolute value of this 1 plus h lambda, or the amplification factor, if this is smaller or equal than 1. If it is larger than 1, it will start either to oscillate or it will blow up without bounds. Yeah, if it will always blow up without bounds. It might oscillate if the amplification factor is negative, but if the absolute value is larger than 1, it will blow up without bounds. So it's unstable. Okay, now this condition of stability, well, because we have this absolute value signs, well, we can rewrite this. So we just substitute that q is 1 plus h lambda, and we get rid of the absolute value signs by checking that it is larger than -1 and smaller than 1. So that's equivalent here. Now we can subtract 1 from both sides of the equation here, from all sides of the equation, let's say, so that we have -2 is smaller than or equal to h lambda, is smaller than 1. And then we have here the following. Now we know that lambda is smaller than 0. We know that h is larger than 0. So h lambda is always smaller than 0, or smaller than or equal to 0. So the inequality on the right-hand side is always satisfied. So we should only take into account the inequality on the left-hand side, and what remains there is that h, so this is a condition on h, that h should be smaller than or equal to -2 divided by lambda, where lambda is a negative number, so this is a positive number, which will give us an upper bound for the h that we can choose in order to have a stable numerical solution. So let's look at an old example here where we actually observed that explicit Euler tends to blow up if we take h if we take h to be too large. So we have this initial value problem. Lambda here is -4. So we have an analytical solution for this initial condition. We have an analytical solution of e to the power -4x, which is stable. We have a negative lambda. Now let's take a look at the numerical solution. using explicit Euler? Well, based upon our analysis, well, we have that the amplification factor is 1 plus h lambda. That's something we found from the theory. But from that, we derived that h should be smaller than or equal to minus 2 divided by lambda. And filling in lambda is minus 4. We find that h has to be smaller than 1 over 2, smaller than or equal to 1 over 2 in order to have a stable numerical solution. And that's indeed what we find over here. So we have an h of 0.4, and we see here that, well, this is stable. So we have a decay of the solution. So it stabilizes, it goes to the exact solution if we increase x, whereas for explicit Euler, whereas for h is equal to 0.8, which is larger than our stability criterion here, so that is not met, we see that that our numerical solution increases without bounds. So even though our analytical solution is stable, if we choose h too large, we get an unstable numerical solution. And this is a very distinct feature of explicit methods. They always have these stability criteria, and they can be quite stringent in some cases. For instance, let's say that lambda was very, very large, so negative but very large, then also this h would have to be very, very, very small. Let's look at implicit Euler, and because implicit Euler, well, we kind of used this previous example as a motivating example for the use of implicit Euler or for the development of implicit Euler. Now, in implicit Euler, well, applied to this equation, well, we have then here the slope that we use in order to update the solution, and the slope is evaluated at time step I plus 1. And we can, well, work this out a bit more and put the y at time step I plus 1 on one side and the y at step I on the other side. And then we find here this factor, this factor that is multiplied with the solution value in the current time step. So again, defining this difference as the difference between the perturbed and the original solution to the unperturbed ODE, we find that the amplification factor in this case is 1 over 1 minus h lambda. Now, let's take a look at whenever this is stable. So similarly to explicit Euler, this is stable if the absolute value of this amplification factor is smaller than 1. So let's write this out. So we plug in this guy over here, put minus 1 smaller than the amplification, smaller than 1. Now we know that lambda is negative since the initial value problem is stable. That's something we defined here. So whenever this initial value problem is stable, so lambda is negative, here we have 1 over 1 plus, because h is positive, plus a number. So this is always something divided by something bigger. So this can never be larger than 1 or smaller than minus 1. So this is always satisfied no matter what your value for h is and no matter what your lambda is, as long as it is smaller than or equal to 0. So this means that this is unconditionally stable. So you can basically choose whichever h you want, and it will be stable if the IVP itself is stable, of course. So looking at this example here, well, we saw that for implicit Euler, we were able to use an h of 0.8 and it still remains stable. And now actually we proved that for implicit Euler, we would actually be able to choose any h and still attain a stable solution. So you can choose your h to be 2 in order to cover the entire interval in one step, and still it would be unconditionally stable. It would still be stable, and that's a very distinct advantage of implicit Euler, is that it is very, very stable. Okay, let's sum up what we learned about stability of numerical methods, we only did a stability analysis of explicit Euler and implicit Euler. You could, in theory, also do this for all of the other methods that we've seen in this chapter. And they all have their own amplification factor. Then, well, what we would find is that we would make a stability criterion based on saying that the absolute value of this amplification factor has to be smaller than 1. And you have to choose h such that that is satisfied. We found that for implicit Euler, this was satisfied for all h, whereas for explicit Euler, we had a criterion for h which it had to be upheld. Otherwise, you have instability. So some remarks. Implicit methods in general are much more stable than explicit methods. Even though implicit Euler is unconditionally stable, not all implicit methods are unconditionally stable. So for instance, if you look at some implicit Runge-Kutta methods, they are much more accurate than implicit Euler. However, they are not unconditionally stable. But that is let's say the general advantage of implicit methods is that they are much more stable than explicit methods. The price you pay is that you have to solve this nonlinear equation in every step when you use implicit methods versus explicit methods, where you can simply evaluate the solution in the next step from the currently known values. Also important to note here is that this stability criterion, let's look at this one for explicit Euler, specifically for the test equation. It can become very restrictive for certain equations. And here for this test equation, let's say that if lambda was a very, very large negative number, minus 1 million or so, that this becomes a very, very strong restriction on the step that you can take in order to ensure a stable numerical solution using explicit Euler. Now in the next video, we will discuss stiff differential equations, which are notorious for having very stringent stability criteria, but still requiring a very long horizon for your integration of the ODE, such that explicit methods become extremely expensive to use for such equations.